Hi everyone, so welcome to class 3. So today we are going to start laws of thermodynamics. I mean, if we are doing thermodynamics, we cannot escape the laws of thermodynamics, right? And so let's get started. We are developing language of thermodynamics, as so just to remind you. And this will be eventually, I mean, this is used in the synthesis of materials, right. So to understand how to synthesize materials, we said first we understand what equilibrium is, and then we see how we can take systems away from equilibrium, and in this process of taking systems away from equilibrium, what is it, so how am I synthesizing materials, right. Okay, so first things first, laws of thermodynamics, let's ignore the 0th law, right. So that's not even a real law. So let's do the first law of thermodynamics. Okay. Now what is first law of thermodynamics? I mean, different people say it in different ways. Energy is conserved, total energy of the universe is conserved, but it is essentially an energy audit, right. So the way it is representable for the systems, for our systems, right, so which I want to grow, is if I lose or gain any energy, right. So this is what is called the internal energy. I'll use the letter U because maybe later on I'll be using E for electric fields and things like that, right. So this is the internal energy, the energy inside of any system. Okay. The way I can lose or gain this energy is either through heat, either my system is taking heat from the surrounding, right, or it is doing work on the surrounding, right. So, so this is heat taken by the system and this is work done by the system. So it's essentially an energy audit, and I think so from all the other thermodynamics courses you may have seen, you would have seen first law in several different forms, but the equation more or less remains the same, right. So du is delta q minus delta w depending on conventions, right. So if you say there is work done on the system, then it becomes plus delta w. Okay. So the way so I interpret this is the only way you can change the energy of the system. Energy meaning internal energy, and what is internal energy? This is so if a system is made up of atoms, let's say this is a crystalline system made up of atoms, right. So I can imagine that all these atoms are nothing but atomic springs, right. These are the bonds essentially between atoms, these are all springs. Okay. Each of these spring is vibrating, right. So each of these spring has a kinetic energy to it, which is half mv square, and each of these springs is vibrating, which means it also has a potential energy which is half kx square, and that together constitutes the total internal energy of my system. So total U is the kinetic energy plus the potential energy of all the atomic springs, let us say. This is just from a rigid this is from a bond model, a spring and bond model, right. Now I can further fine grain it by saying, oh no, there are electronic degrees of freedom, there is an electronic internal energy, there is a phononic there is a vibration internal energy. So I can put in all these things and add up all the various factors, right. So the more atomic I go to, the more things I see. There is electronic energy, that is your electronic band structure, there is a phononic energy, that is your phononic band structure. All these things together comprise the internal energy, the total internal energy of the system. Okay. Now, alright, so I have this internal energy. How should I change this internal energy, right? The way to change this internal energy, the way to make these springs oscillate more vigorously or less vigorously, right? So that is, I am increasing the kinetic energy of these springs, is by heating them, right? So I supply heat, right? Or I do some mechanical work, I apply pressure, I do some kind of work so that so these springs their potential energy, right? How do I change the potential energy of these springs, right? So I can do some work, I can extend these springs in a certain way, right? So is either by sending in delta Q or delta W, right? So that is the only way I can change the total internal energy of this system. Let me write it in a different color. So how do I change the energy? So delta Q or so let me write it in green, let us say, or delta W, right. So these are the only two ways in which I can change the internal energy of the system. Now first law of thermodynamics does not tell me the internal energy, the reason for internal energy is so and so. Here I am actually trying to give you an atomic picture of what is the reason for internal energy, but first law of thermodynamics does not care. The reason can be whatever form of energy, right. So if I have some electrical energy inside a capacitor, right. So internal energy of a capacitor, self energy of a capacitor of an electrical system, right. So that is the internal energy is nothing but half CV square or half capacitance times the voltage square, right. Or so the essentially the system so first law of thermodynamics does not tell me what is the origin of this internal energy. It can be electrostatic, right. So electrical system or electrostatic system, right. It can be magnetostatic, it can be just an the spring mass model of an atom, right. So whatever it is, any system has some internal energy, and the way I change the internal energy of that system is by putting in heat or taking out heat or doing work or making it do work on the surrounding. Okay. All right. Now the question is, all right, so why are we classifying this thing as so essentially there is some energy transfer, right. So I have to change the energy of the system. And that I am saying I can do it either through heat, I am artificially dividing it into heat and work or doing work on the system. Okay. So then the question is, what is heat and what is work, right. Turns out heat, so both of them are some kind of energy transfer components, right. So only with heat and work I can transfer energy between system and surrounding, right. So this heat turns out to be what is called an incoherent form of energy transfer, and the delta W is a coherent form of energy transfer. It's a much nicer form of energy transfer. Okay. And heat is a very noisy form of energy transfer. Okay. Now let us try to understand that with a simple example. There is a nice way of illustrating this, right. So and how do I understand heat and work, right. So this is always a question that we have when we do thermodynamics. Now all right, so let's go back to this example that everyone gives of a piston. So this is a piston, right. So these are some gas molecules. Okay. Now I am going to expand this piston, right, or this gas is doing some work on this piston, right. So the piston is actually moving in this direction. Okay. So gas, some work on the surrounding. How much work is, let's ask the question, how much work is gas doing on the surrounding, right, or gas doing on the piston or piston doing on the gas, it's one and the same, right. So now on the piston, right, on the piston there is a force that the gas is applying, right. On the piston there is a force that the gas is applying, work done. by the gas on the piston, right. On the piston, right. So, if I just do a free body diagram of the piston, there is a force that is being applied by the gas, right, and that force is letting this piston displace by an average amount of x. So, this piston was here to start with, and then the final position of the piston is somewhere here. This is okay. So, Fx, right. So, F is also some kind of, I will write it to be average force, but we will know what that is later. So, this is the work done or delta W done by the gas on the piston. Okay. All right. But if I ask you the question as to what is total internal energy change on the piston, what are you going to say? So, then I am going to do a coarse graining of the a fine graining of the piston, right. Just like I have earlier divided my entire material into set of atoms with springs and other things, I am going to look at the atomistic model of what this piston is made up of. Okay. Now, this piston is made up of several atoms or so whatever molecules, right. At these are all the various molecules in this piston. Okay. Every molecule, so a gas molecule comes and hits this part, another gas molecule comes and hits this part, another gas molecule comes and hits this part, and so on. Different gas molecules are applying different forces, right, at a given instant at different gas molecules are applying different forces at, so this is I equal to 1, this is I equal to 2 on different regions of the piston. Fi is the force applied on a piston molecule or on a piston section, molecular section, let us say, okay, at a certain instant. Okay. Like that, so this is 1, 2, 3, I have I such sections, I molecules, right. So, how many ever I can be large number 10 power 20, 10 power 30, whatever it is. So, Fi is the force applied, right, and each of these forces is slightly different, right. So, different molecules are applying slightly different forces on every part of the piston. Okay. Now, if I have Fi, this particular part of the piston would have extended, right. So, let me draw it here, this particular part of the piston I equal to 1 would have extended by xi. Okay. An average of Fi xi tells me how much is the change in the internal energy of the piston. Right. So, that is so F force times displacement, that is the total energy, but force times displacement of every atom, I am counting the force times displacement of every atomic section or every molecular section, right. There is some gas molecule comes hits it, some gas molecule comes hits the second part, second thing, some gas molecule comes hits the third part, fourth part, and so on and so forth, everything slightly different forces and everything is displacing. But everything is displacing to certain extent xi, right. So, Fi xi, right. So, this is the total work done on one gas molecule. So, second piston molecule, third piston molecule. So, F1 x1 is first piston molecule, F2 x2 is second piston molecule. So, I calculate all this energy, right, and then I take an average of it, that gives me the average internal energy, right. So, average change in the internal energy. Okay. So, divided by or an average of it divided by I essentially. Okay. All right, good. So, okay, sorry. Then the question is, I have an internal energy which is given by Fi xi, I have delta W which is given by capital F times xi. Now, what is capital F? Capital F is the average force on the piston. What is the average force on the piston? Average force is just average of all the forces on all individual molecules, right. So, this I can write it as Fi xi, where these arrows means it is the average. Okay. So, then if I look at so if I write this is the work done by the gas molecule on the piston, right. So, this is the work done on the piston and so what is the heat that is given to the piston, let us say. So, then that heat delta Q, so this is the total energy which is Fi xi minus small fi small xi, right. So, that will be the total heat transferred from the piston to the surroundings, right. So, or given to the piston, essentially the sign is such that this is given to the piston, right. Okay, this is not 0, right. Now, what is this saying? Essentially, let us plot how the piston is displacing with respect to time, right. Now, xi means every individual section of this piston, right. On an average x, the entire piston on an average is going like this, right. So, it is having the straight line motion, right. So, it is increasing, the average x is increasing, okay. So, the total work on the piston is increasing, but every individual molecule is actually doing on an average increasing, yes, but x1 is sort of going like this, right. It is not so the xi is not exactly, there is some noise on the top of this average motion, right. So, there is average motion, but so this thing is vibrating a bit this way, that way and on an average moving in this fashion, right. So, this molecule essentially on an average is moving by x, but it is also vibrating across x, right. So, and that vibration is because of this variable force that is coming up, okay. Now, similarly x2, how is x2 going? x2 is also going in some other so let me put this way, x2 is also going in some other way, x3 is also going in some other way like this, right, and so on. Now, if so each individual trajectory, right. So, xi let us say of the ith molecule of the piston is going this way. So, I am going to write it as an average x, right, as a function of t plus a noisy x, right. So, this is the variance or so this is the noise in x as a function of t, right. So, what is this saying? Every piston molecule is on an average moving in this fashion, right. It is not just doing an average motion, it is also doing some noisy motion about the average, right, because everything has slightly different force, it is different from the average, right. So, slightly different from the average, Fi is not exactly the average force, right. Similarly, piston molecule 2 is also doing it is actually going in this fashion, right, but it is oscillating, it is noisy motion, right. So, it goes, jerks, comes back, goes, comes back, goes, comes back and so on and so forth. So, I have some sort of a noisy motion, right. Now, this so the work done actually tells me is only this part, right. This is an average motion, right. So, work done on an average moves the piston, right. So, this is a coherent form of energy transfer from gas to the piston. What about the rest of it? The incoherent form of gas energy transfer which is so which gives rise to this noise, okay. So, the incoherent gives rise to this noisy motion of the piston, or in other words that is it is some kind of a vibration or noisy vibration, right. So, it is not some coherent vibration, and that form of energy transfer is your heat. If I am heating it, I increase the vibrations, right. So, that is essentially what it is. The gas is not just transferring energy in the form of coherent work done, right. So, how are you transferring energy from the gas? Every molecule is transferring its energy, right. Now, every molecule is on an average giving a force F, but there is some variance about F, right. that variance is going to vibrate this piston, right, about the average, and that vibration of the piston is nothing but incoherent energy transfer, and that is why the piston gets heated up or cooled down, right, depending on, so in this case, so the heat is being transferred from the gas to the piston, right. So now what is the total internal energy change in the piston? Total internal energy should include this average motion plus every molecule I should keep a track and see its noisy motion, right. And then so that sigma Fi xi, this is the total internal energy change, that is Fi xi, this is the work done, plus I mean I can just write it as Fi xi minus Fi xi, this is the noise or incoherent energy transfer, or this is the heat, yeah, the heat transfer essentially. Okay. So this is how you interpret the first law of thermodynamics. You have work done, I mean, so how can you change the internal energy of the system? You have to do work on the system, and work done is a coherent form of energy transfer. You have averages. Coherence is all about consistent motion or a coherent motion of the piston in this case, right. So in this case it is a very coherent motion of the piston, right. The incoherent motion of the piston, however, is embedded in the heat, right. So that is the heat transfer. So both work done and heat transferred to the piston together is going to increase the internal energy of the piston, and that is done by the gas. In this case the piston is my system, not the gas, okay. So typically gases are your system, okay. So that is a good way of interpreting, I mean, so at least understanding the first law of thermodynamics, okay. So so this also explains us what is work, what is heat, okay. Thank you very much. I will see you again in the next class.